Okay,
Yeah,
so
so week
four
4 is
so
so
we
we
are
are on week
four
4
now.
now.
So
So
I
I
hope
hope
everything
everything
is
is
audible
audible
and
and
fine.
fine.
Uh,
Uh,
Yes,
I'm
I'm
audible.
audible, right?
yes, sir, audible.
Mhm. Let me go to the course.
మసలానే కాయ ప్యాకెట్ వేసినావా
Okay. So this is the assignment from the last year's questions. So I'll be discussing all these things, all these questions one by one. So you can try to solve it. So this week's content was on SBM. Yeah, so hopefully like everyone went through the content and got a good idea of the content. And yeah, so you should be able to solve these questions. And I'll be solving these things one after the other as well. I don't think the pencil is working here. So I'll be putting these questions there and like solving it in my notebook. So yeah, so this is your question. Just put it there, it will be better. This is the question. Oh. Sorry. So this is your question. This is the first question, and there are like 8 questions this week. Okay. So if we talk about support vector machines, I am audible, I hope. Yeah. So if we talk about support vector machines, in support vector machines, we so let's say there is a data plane. Sorry. Let's say there is a data. There are data points like this. Let's assume that we're having linear data. So what we do is that we try to find a line that separates these 2 data points, and sorry, that's not a very good line. Yeah, this is a very good line. So that separates to these 2 data points, and what we do, we actually minimize the distance. So we sort of like find a support vector that is perpendicular to the line. Support vector from 2 points that is perpendicular to the line. So like this. They are called the support vectors. These vectors are called support vector. We try to minimize the magnitude of this vector in a way. So the more we minimize the margin, the more closer will be the line, and it will be a better classifier than the other. So let's say like if we don't minimize this, then this also can be a line, and this also can be a perfect. According to this point, this is also a good classifier, but it is not classifying all the points correctly. So that's why so we need to minimize the minimize this one, minimize the magnitude of this vector, and we then after solving this equation, that equation, all the SVM maths, we'll get the separating hyperplane, or this is called the separating hyperplane. That is like perpendicular to the points. Sorry, that is like perpendicular to the support vectors. So the question it is asking now is that for a 2-class classification problem, we use an SVM. For a 2-class classification problem, we use an SVM classifier and obtain the following separating hyperplane. We have marked 4 instances of training data. Identify the point which will have most impact on the shape of the boundary on its removal. Answer I'm getting is 1. Anyone else? Yeah, 1. So correct answer is, yeah. So sorry. The correct answer is 1. The reason is that the nearest point define the shape, and out of this 4 points, the nearest one is this one. So this will this way support vector, and this will define the shape of the line. So insert. So this is the second question. You may try to solve this one as well. It's a theoretical question again, and should be able to solve it. It's pretty standard. Meanwhile, I'll just pull out other questions as well. n+1 false. What's false? Okay, no, the question number 2 only. Sorry. That's question number 5. But yeah, okay. Question number 2 is consider a soft margin. Consider a soft margin autoencoder, so soft margin SVM with a linear kernel and no slack variables. Okay, trained on endpoints. The number of support vector returned is k. By adding one extra point to the dataset and returning the classifier, by adding one extra point to the dataset and retaining the classifier, returning the classifier, what is the maximum possible number of support vectors can be returned? Training parameter C. Yeah, so it's a good question. So can someone explain this? Like, I know the answer is n+1, but can someone explain this, how this is coming in the chat?
The maximum number of support vectors is equal to the total number of data points, right? That +1.
Okay, so can someone tell, like, if oh, sorry, 1 second, give me a second. I'm just making a scenario. I'll just ask a different question. So let's say, like, we assume that the point, yeah. So if so there are endpoints here. So there are endpoints of different class, and so we created a software classifier like this. So this is a latest software classifier with endpoints. Okay, and there are k support vectors. There are k support vectors, right? Right. Yeah, so there are k support vectors. That means k should be less than n. I don't know why they haven't given it. What should be less than or equal to n? There are k support vectors. So then it is asking that if I add another point, then what will be the number of support vectors after adding another point, right? So if I add another point, the point can go here, here, on the boundary, here, anywhere, right? But if I consider this point, like, which is very far away from the distant boundary, then it might not be a proper point to be a support vector, right? If the new point lies in the distant, if the new point is lies very far from the distant boundary, it is less likely to become a support vector, because support vector are the one, the vector from that point which supports the hyperplane, right? But if the point lies on the distant boundary or close to it, it's highly likely that it will become a support vector. And this is because support vectors are the point that define the distant boundary, right? So if it is on the support vector or like near, so it will form a support vector. Since it is saying that what is the maximum number of support vector is possible, we can go ahead and say that the point, like, since we can say that we'll choose the point close enough to the boundary so that it will make a support vector. Another thing is that why it is not k+1. So initially it was k, and let's say adding another point, it should be k+1, right? I mean, just if this last one makes support vector, the initial number, so the final value should be k plus 1, right? So why it is so, even if it makes or not, it do not makes, it should be either k plus 1 or k, right? So why it is n plus 1 or n now? Why it is not k plus 1? Why it is n plus 1? Can someone tell?
We're talking about data points, no, sir.
Yes.
So that's why I think it's.
No, so the question is that the number of support vector returned is k. So for n number of points, the number of support vector is k. So if I add one more point, let's say that point is leading me to the support, like, that point is giving me another support vector. This can be k plus 1, right? Why it is n plus 1?
Will the support vector change in that case, or is that why the
Yeah. So the
points
thing is that, yeah, so
contributing
the
to-
point, I mean, the distance boundary can change as well based on the point that we put. So the maximum is n plus 1. So the initial answer is correct, like what Aju said, is that, like, given number of point, if you just ask like what is the maximum number of this possible, it is n plus 1. But since it is given in such terms like k and k plus and all these things, then I just added some bit of complexity over there. So the smoothing parameter c that is given here is that the c parameter is soft margin. C parameter is, like, it's generally in the soft margin SVM. The C parameter in the soft margin SVM controls the trade-off between the maximizing the margin and minimizing the classification error, right? So if you make the value of C higher, it will prioritize the minimizing the classification error, right? Which will lead to more points becoming support vectors. Okay, so if you lower the value of C, that means SVM will prioritize maximizing the margin potentially, resulting in like fewer support vectors. So the lower C, the lower the number of C will lead to lower the number of support vectors. So we can also change C, right? So by changing all these things, the maximum we can get is n plus 1. So the answer would be n plus 1, even if it is k for n. So it's just given, right? Anyway, we'll go to the next question. Next question is, consider the dataset given below. Feature 1, feature 2, 0, 0, 0, 1, 1, 0, 1, 1, 1. It is coming as A, B, B, A. Okay. And claim is that the perception learning algorithm can learn a classifier that achieves zero misclassification. Learns a classifier that the claim is that the perceptual learning algorithm can learn a classifier that achieves zero misclassification around the training data. The claim is A, true, B, false, C, depend on the initial weights, D, true only if we normalize the feature vector before applying PLN. I think someone answered it as false, I guess, before. Yes, one answered it as false, but yeah, everyone else can try. C, depends on the initial weights.
Sir, in perceptron algorithm, randomly we are going to choose the weights, no, sir? So that's why it cannot
Yes.
depend on initial weights. So in order to update the weights, no, sir, in order to remove that misclassifications error.
No, so you said
I think it's false, sir, for this answer.
yeah, it will be false. Okay. So do you know why? Why perception learning algorithm cannot. So it is saying can learn a classifier. And it is saying that it cannot learn a classifier. Do you know why?
It is a XOR function, I guess.
Yes. So yeah. So since it is a XOR function, it will not be able. XOR function is not linearly separable. So a linear algorithm like perception learning algorithm cannot learn a classifier for that. So XOR function is, so if you here go here, so it's, so 0 0 is class A, right? 0 1 0 1 is class B. Then 1 0 is, sorry, 1 0. 1 0 is class, sorry, 1 0 is class B, and 1 1 is class A. This is not linearly separable, right? Not linearly separable. That's why it is false. Next question. Consider the following data set. This one. Note X is the feature and Y is the output. Which of these is not a support vector when using a support vector classifier with a polynomial kernel with degree equals to 3, C equals to 1, and a gamma equals to 0.1? We recommend using sklearn to solve this question. Let me set up the sklearn in my system, and then we'll solve this question one by one. Okay, it will be better to solve it in the in the laptop. Okay, I'll just switch the screen sharing. XOR function cannot be learned. No, XOR function can be learned, but XOR function cannot be learned using MCP. Sorry, what is that? PLA, perceptual learning algorithm. Okay, it cannot be learned using the perceptual learning algorithm, but in general, it can be learned. Okay. So yeah, so I think the other screen is visible now. How the recording is going. Yeah, okay. Okay, perfect. We'll create a new file here. CM file. Okay, so my screen visible, right? Yeah. So did you get a chance to look at the question? I'll just yeah, I'll just show you the question once, and so make sure that you understand the question. Then we'll jump on to this solution. Okay. This is the question. Try reading the question. I'll come back in a second. Then we'll go to the code and we'll code this out to find the solution. So yeah, so let's say the code screen. Yeah, it is saying that so this is a data set X and Y pair. Which of these is not a support vector when using a support vector classifier with a polynomial kernel with degree equals to, 3 and C equals to 1 and gamma equals to 0.1. C equals to 1 means we're giving more priorities for classification. So if we start solving this using the sklearn, not sure how to import that. It might take some time. Okay.
Can you just type it, sir? The array?
Sorry.
No, the array we can just type it or matrix.
Hello. Hello.
Hello.
Yeah. You saying something?
No, nothing.
Okay. Let me check. Actually, I'm not. I'm like remember the exact code, but let me check it the internet. What is this SVC? Yeah. So SVC. Kernel equals to polygon or linear? Polygon, right? And then degree equals to 3, C equals to 1.0, I guess. Yeah, degree equals to C equals 1.0. Anything gamma, I guess. Gamma equals to 0.1. Yeah. Sorry, you startled me. Okay, so then we'll define our X and Y. Okay, so X equals to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I can just write np.array np.array range 1 to 10. It will make sure that it will go to 1 to 10. Let me import numpy as well. Let me check.
4 and 8 are skipped in that.
Okay. No, I don't think 1 to 3. No, 3 is skipped, right?
3 is
1
skipped.
to
3 and 8.
Okay.
Yeah.
So we cannot use this. But then 1, 2, 4, 5, 6, 7. I think 8 is there. No, 8 is not there. 7, 9, 10. X, Y would be yeah. So Y would be similarly np dot array and it's 1, 1, minus 1, minus 1, minus 1, minus 1, 1. So 1, 1, and then classifier equals to model dot fit x and y. So this is like defining the model. And it's like defining the data, okay, and this is like fitting model for training, okay. Once it is done, we can obtain the support vector, okay. So 10 support vectors, okay, and support vector will be model dot support vectors, and sorry, not model dot support vectors, should be classifier dot classifier. Sometimes the recommendation fails, and then you have to print the support vectors, right? Let me run this code here. Okay. If I run this, wow, 3. No model name number. It's not good. I don't know like what happened to Conda, but it is not working. Let me run it in a different environment. I'll connect to a server and run it there. Sorry. Yeah, So I'll just change it. Why it is not showing anything? Okay. I found it back. Okay, so I need to reset, I guess. Yeah. So you got the support vectors 5, 6, 7, 1, 2, 9. Okay, so if you run it again, same output. Okay. So the question that I had, which of the following is not a support vector when using support class? If I'll share the screen now here. Yeah. So which of the following is not a support vector? The answer is 5. 10 is not there. 3 is also not there. 1 is there and 9 is there. So it should be 3 and 10. But the solution is 1. Select. I don't know how. The code is giving us this one. You saw it, right? 5, 6, 7. Yeah. 10. Yeah. 5, 6, 7, 1, 2, 9 are support vectors. According to that code, let me check. Did I pull the correct code or not? Yeah. 1, 1, minus 1, minus 1, minus 1, minus 1, 1, 1, 1, 2, 4, 5, 6, 7, 8, 7, 9, 10. And yeah, it's all good. And should be 1, 10 according to this one. Let me change the value of C. No, I don't need to change it. There's nothing to infer. Just question. Okay. Let me share the screen from here again. Let me. Yeah, let me share the screen again from here. Screen, start broadcasting. Yeah. On to the next question.
So can you share that code also?
I'll share it in the chat.
Okay.
But this is a single option answer, right? Can't we do?
Yeah, I mean we saw the code. So the code was, wow, why it is not sharing this? Yeah, so the code was written based on the data, right? So we just trained the SVM and we printed the support vectors for this data. It is coming as 2. Might be a mistake by the question setter, but the code cannot. We ran it two times and we entered the correct value. and the code is like just the implementation of the algorithm. So it should give the correct answer, but not sure why it is not working.
Okay.
Yeah, coming to the next question, question 5. I think it's a relatively easier question than the others. I should be able to do it.
So here one doubt, this order in which the points are presented means it's always X and Y being swapped, right? It's not like you're jumbling the data and giving it, right?
Sorry?
No, the question, the third point, order of points, what they're referring to, is it like you're jumbling the data or it's like X?
Yeah, often separate have depend on the order in which the points are presented in the training process. It's saying that, yeah, so something called like you shuffle. So whenever you are training, so the training data are generally like arranged like 10 first 10 or first, let's say 10% would be for class 1, then 10% would be for class 2 and so on. So what it is saying is that when it is trained, it always jumbles the data before presenting it in front of the model. So it's like shuffling data before it present in front of the model. So that is the thing that it is saying here. Okay, so let's just see the solution. So which of the following is are true for the perceptron classifier? So we had seen the perceptron learning, I think, perceptron classifier. So perceptron classifier like is like linear, can separate the linear data. So it's saying that it can learn or function. So or function is linear, right? So or function is linear. Yeah, So false, true, true, true. So it's linear. So it can be learned using the perceptual learning algorithm. Then AND function, similarly, AND function is also linear. It can be learned. So A and B are correct, right? The obtained separating hyperplane depends on the order in which the points are presented in the training process. The perceptual learning algorithm is dependent on the order in which the data is presented. So the thing is that if you look at this one, this can be hyperplane, this can be hyperplane, this can be hyperplane, this. So all these tiny lines can also be hyperplane, right? But the algorithms, the hyperplane on which the algorithm will end up depends on the order in which the data is presented. So you're saying that the obtained separating hyperplane depends on the order in which the points are presented in the training process. It is true. The resultant hyperplane would be different, like, will depend on the order it is presented, but the actual results, like the accuracy, so the accuracy, or the F1 score in case of anomaly detection, so all these metrics will nearly equal to all the metrics for all other equals to 1 to, let's say, infinity, for infinite number of permutations of the, like, infinite number of shuffling. So if you shuffle it in a like, n different ways, n different ways, the accuracy will obtain for a particular model for different shuffling will be similar, but the hyperplane that it will learn will be different, since there are a lot of hyperplane giving the same value. And fourth point is, for a linearly separable problem, there exists some initialization of the weights which might lead to non-convergent case. It's saying that if the data is linearly separable, there might be a case where it will not be able to classify it correctly, like, saying that solution can be this. The answer is wrong. This truth is wrong, because if the data is separable, the perceptual learning algorithm can learn it. So ABC is true and D is false. Come to the next question. Yeah, sorry. Yeah.
Oh, sorry. The third one, if all the points are given, then will you not get the same hyperplane every time? I mean, if I'm giving A, B, C in a different order, A, C, B, it's still having all the points, right? I didn't get that.
No, in case of SVM, the support vectors are like decided after looking at all the data, right? So in case of perceptual learning algorithm, it's more like artificial neural network, or like, it's like ANN. So it learns, so it minimizes the loss. So it will see one point, it will minimize the loss against that point. Then it will go on to the another point, and it will try to minimize the loss against that point. So the distance boundary, let's say this is the initial distance boundary, and like these are two points. So if the distance boundary, like if the points that coming next, like come in different order, for each point it will adjust. Like if you put it in that way, like for each point you are minimizing the loss. So for each point it will try to reshape itself. So hence the order in which it is reshaping, like the order in which the points are coming, the final hyperplane would be different, because like it's not about like who is giving support vector for this hyperplane to stand. It's like creating a balance between the existing points. So it's like for probability of finding hyperplane, probability of finding a separating hyperplane given the current value xi. So I mean it's a sequence. How the position of this hyperplane, like, moves the sequence. So if it is here, you got the idea, right? Like, the current state of the hyperplane depend on the previous state.
Yes, sir. Got it.
not the entire thing. I'm not going to explain it correctly, but yeah, got the idea. So if you train very large deep neural network models, what we do generally is that we generally shuffle the data first, right? So that we don't want the algorithm to learn a particular hyperplane, but we want them to learn like different hyperplane, like a generalized hyperplane, which will able to which will be able to separate everything, this the existing data as well as the new data. So what we do is that we run iteration of the algorithm. Like it's not just run for one iteration. Same number of data is fed into the model multiple times, like iteration 1, iteration 2, and iteration 3, and so on. Each time when we are feeding it to the model, we shuffle the data first, then we feed it. So in case of like 4 data points, it's in case of like 10 data points, it's very easy to get the same shuffling or adjusting all the permutation of these data points. But in case of like when you have thousands of data or millions of data points, you cannot exhaust everything, right? So that's why like we try to find a hyperplane that is supported by multiple shuffling operations. So shuffling is a good thing, and that reduces the bias or the reduces the um, overfitting problem. Okay. So going to the next question. It's an interesting question. I try to solve it because if you're giving me answer in like 2 minutes, I think it will take time more than 2 minutes. Okay. Yeah. So we'll solve this question. So optimization problem are a bit tricky, and it has a different course as well. So the optimization function, I hope you have learned it in the SM. The way I learned it is it started from SBM, and I then took a different course for it, sort of. So it's written minimize this x square plus 1 subject to the ST is subject to the constraint x minus 2 and x minus 4 less than equals to 0. Okay. So first thing is that you are minimizing this one, and the constraint is that the subject to the constraint is that this x minus 2 and x minus 4 should be less than equals to 0. Like it's sort of also it is also sort of minimizing. You're saying that it should be less than equals to 0. It cannot. It's like there's a cap on this thing, right? So the Lagrangian method tells that if both the term is minimizing, what you can write, like like both of the term is agreeing, what you can write this and this. So this thing is that this thing might not be convex every time. So what you can write is that the Lagrangian conversion of this is like you take x, okay, and lambda is a Lagrangian coefficient. You L, so this is f of x. So this is your f of x, right? And this is f of x. So you convert that f of x to Lagrangian of x and another parameter lambda, and you are telling x square plus 1 plus lambda times x minus 2, x minus 4. So this can be written as this. So this is the Lagrangian form, where you can add a Lagrangian coefficient to represent the what? To represent the minimization problem, like two-step. So two-step minimization problem to this one. Okay, and if you expand this, it will be x square plus 1 plus lambda x minus 2 lambda, and sorry, let me just first expand this. This lambda, and this is x square minus 4x minus 2x plus 8, right? And plus lambda x square minus 4x minus 2x, 6x minus 6x lambda, then plus 8 lambda, right? And that will be equals to, you combine this and this, x. Okay, so it should be lambda plus 1 x square and minus 6 lambda x plus 8 plus 8x, right? Plus 8 lambda and plus this one. Okay, so this is the form of x square plus bx plus c. Okay, and you can, it is equivalent to saying that it is equivalent to minimizing lambda plus 1x square plus minus 6 lambda x plus 1. Okay, it is similar to minimizing this without any constraint. So from this equation, you can say that option C is correct. So the Lagrangian can be written as this one. So option C is correct. Okay. Option C is correct. Then the second thing is that you have to find the dual objective. So dual objective is that minimizing this should be equals to maximizing some another equivalent term. Okay. So we can find the dual objective. So you have to, so after converting into the Lagrangian form, you have to find the dual objective. So every Lagrangian form, so Lagrangian form is actually used to making a non-convex constraint into convex constraint. So it's similar to like that. Like so if this constraint is very hard to solve, like let's say like you're solving one equation minimizing one thing, subject that x should be less than equals to 1. So the constraint is like that. Minimizing x square. Okay. This is y equal to x square, right? So y equals to, yeah, so this is y equal to x square. At y equals to, yeah, so this is y equal to, sorry, this is, let's say y equals to x square, right? And your constraint is the constraint is x should be greater than, sorry, constraint is x should be greater than equals to 1. Let's see. So let's say this is the function and this is the constraint. So this is the function and this is the constraint. So when you are minimizing, so I hope everyone is with me. So I'm just boiling it down. I'm not sure like how strong you were in the Lagrangian and all these things. So I'm just boiling it down. So minimizing f of x.
That x greater than 1, how did you get x greater than equal to 1?
So let's say this is, so this is not related to the question. I'm just creating a scenario where let's say this is our case. Like we have to solve this optimization problem, minimizing f of x so that x greater than equals to 1. And f of x here is, let's say, x square. Okay. So minimizing x square such that x greater than equals to 1. If you look at minimizing x square, so this is the minimum point, right? So minimum point x equals to 0 is the minimum point, right? But when you put this constraint x should be greater than equals to 1, so the valid set lies in this side, okay? And all these things are not valid for this constraint. So hence this will not be the smallest point. The smallest point, since it is just valid in this range, so it will be here. So x equals to, so for this solution is x equals to 0. For this solution is x equals to 1. So what happens is that sometimes this constraint is not very nice. So the constraint can be non-linear or non-convex. So if the constraint set is non-convex, we cannot solve it directly using this technique. Hence, we use the Lagrangian method. So you can learn more about Lagrangian method and Lagrangian technique for solving the convex optimization problem, where the constraint set is non-convex. So after applying the Lagrangian here, what you can do is that you can so when you do the Lagrangian, you basically convert this non-convex equation to a nice convex equation. This is the convex equation, and it is now solvable. Okay, so option C is correct. Out of A, B, and D, we need to find like which one is correct. So second thing is that we have to find a dual objective. So Lagrangian duality says that when you have a function with a minimum, sorry, let me drink some water. So, okay. So okay. So sorry for taking a break. So Lagrangian duality says that now you have converted the this constrained optimization problem to a unconstrained one. Okay, so we cannot, if the constraint set is non-converse, you cannot add the like this, not like there's a term for that. Not like not so simple constraint to the problem. That's why we expand it to a unconstrained optimization problem by introducing Lagrangian multiplier or the Lagrangian coefficient. But the problem is that now we have another parameter to solve. We were minimizing this x, right? Minimizing the function for finding the value of x. Now we have another parameter, that's lambda, right? So we have obtained this one unconstrained, but now we have to find. So but now we have to find a way to solve for lambda. So if we can find the lambda, then if we can put the value of lambda, then we can solve for the minimizing the x. Because see, minimizing this equation is very easy because it's same as x square. So the equation is similar to x square. So here you see it is x square, right? If you just give me the plot of x square, I can say that okay, this is the minimum point, and this will be similar like x square plus x plus 1, which will be a quadratic function, and quadratic function from the graph you can solve it, right? But there is another parameter, that is lambda, right? So lambda, so the lambda should be solved first, right? So we need to find a way to solve the lambda. So to solve the lambda, we need to find the dual objective. So what is dual objective? Dual objective is the objective that solved for lambda. So dual objective is g of x. Sorry, g of lambda. Okay, so this is the dual g of lambda. So to find the g of lambda, we need to okay. So the steps that involved in this Lagrangian thing is that the first step is that the Lagrangian yeah, so the steps is that like formulate the Lagrangian. So first, so we first write down the Lagrangian function, which will include the original objective x as well as the constraint multiplied by the Lagrangian, that is the lambda. Then we'll find the dual problem. Dual problem is we can find the dual problem by maximizing the Lagrangian over the Lagrange multiplier. And third is to solve the dual problem, then solve the primal problem. So in this thing, if we put it here, so there was an original problem f of x, right? We need to minimize that. So to solve this, we introduce Lagrangian f and lambda, right? Then we'll find the dual function and solve it. Sorry. Yes. Then solve g of lambda. Then solve f of x. So these are the steps. We have f of x, we have found this, then we are going to for g of lambda. G of lambda will obtain by maximizing, the function Lagrangian over the Lagrange multiplier. So maximizing L, x and lambda over lambda, the Lagrange multiplier, right? So g of x, for finding g of x, what should we do? We need to maximize this one, right? How to maximize this one? Del L by del lambda. That will be equals to what is our L? L equals to lambda plus 1 x square plus minus 6 lambda x plus 8 lambda plus 1, right? So dl by this would be 2x and this is 1 plus lambda. Okay. Then before this it will be minus 6 lambda plus 0. Before this it will be 0. That implies six lambda. And so for maximizing, we need to equate this to 0, right? So 2x 1 plus lambda will be equals to 6 lambda. 2x plus 2 lambda, 6 lambda. 2x equals to, no, sorry. This is 6 lambda. 2x plus 2x, sorry. 2x plus 2x lambda equals to 6 lambda. That implies no. So 2, 3, x equals to 3 lambda by 1 plus lambda. Okay. Okay. And so from this, we can say that g of lambda will be equals to so you have to put this one in this. Okay. So that would be let me put that. If I put it there, so it will be lambda plus 1. X square is 3 lambda by 1 plus lambda square, right? Nope. G of lambda. G of lambda. Two of lambda 6. 2 of this 6. 6. No, I have to put it here. Sorry. Here. Try. It's too complex. We'll put x. Sorry. G of lambda will be equals to this 2 into x minus 6 lambda. We put Yeah, so this will be 0. It's no point. That's, yeah, so since this is okay, so since this equation is same as this one, right? We just rearrange this. Let me try putting it here. It will be easier to calculate. So,
अब तो सुनिए, अब तो पता लगेगा। हाँ ठीक है। हाँ ठीक है। हाँ जी। सही।
so this cube. Three lambda by 1 plus lambda. Okay, let's just proceed. If I multiply this, it would be 3 is 9 lambda square by, if I multiply this 1 plus lambda square, and this with this, it will be minus 12 lambda by 1 plus lambda, this with this, minus 6 lambda by 1 plus lambda, this with this, plus 8. Okay, this will be 9 lambda square by 1 plus lambda whole square plus 1 plus, if we multiply this lambda with this one, it will be 9 lambda cube by 1 plus lambda square minus this lambda with this. So this is minus, it will be minus 18, minus 12 minus 6, minus 18 lambda square, right? 18 lambda square by 1 plus lambda, 1 plus 8 lambda. Okay. So if we rearrange this, it will be 9 lambda cube by 1 plus lambda square plus this and this will be added. So if I add that, the base is not same. Sorry. Yeah, the base is not same, so we can add it, right? So the plus, let's just plus, the base is 1 plus lambda square, 1 plus lambda, the base will be 1 plus lambda square, 1 plus lambda square times 1 plus lambda is, so it will be 1, so 9 lambda square minus 18 lambda square times 1 plus lambda, and plus 8 lambda plus 1. It will take a bit of time, so hold with me. So it will be 9 lambda cube by 1 plus lambda square plus, it is minus 18 lambda square into lambda. It will be, so this, let us expand it, 9 lambda square minus 18 lambda square minus 18 lambda cube, 1 plus lambda square. Okay, so here, I think I missed one term. X square plus 1 Anyway, so it should be minus 9 lambda square So I think you can spot one mistake, I guess. Somewhere this should be cancelled. I'm not sure why it is not cancelling. I missed something somewhere maybe. If you are with me, you can point it out. It should be cancelling. 3 lambda by 1 plus lambda. So this was the equation. 1 plus Oh no. This was the equation, right? Let's just put it here. We'll try. Just give me a second. I think taking much more time than I should take. If I cancel this, the answer should be equivalent to minus 9 lambda square by 1 plus lambda square plus 8 lambda plus 1. This should be the answer. If I cancel this one, since it is not cancelling, let me write down that again. What is that? Lambda plus 1 x square, lambda plus 1 x square minus x square minus 6 lambda x minus 6 lambda x plus 8 lambda plus 1. Okay, let me just put x square is x is 3 lambda plus 3 lambda square by lambda plus 1 square minus 1 square minus 6 lambda into x is 3 lambda by 1 plus lambda plus 8 lambda plus 1 is equal to 9 lambda cube, 9 lambda square into lambda, 9 lambda cube plus 9 lambda square by lambda plus 1 square minus 18 lambda square by 1 plus lambda plus 8 lambda plus 1. This also coming as minus 18 lambda, so it is coming also as 9 lambda cube by lambda plus 1 square and minus 9 lambda square by 1 plus lambda plus 8 lambda plus 1. Okay, so this is the final equation that is coming, so it should not cancel here. So this is the not correct. So this should be the final answer. It should be coming. I hope everyone is getting this. And so after getting this, so we can say that z of lambda is equals to 9 lambda cube by lambda plus 1 square minus 9 lambda square by 1 plus lambda plus 8 lambda plus 1. But this is if x equals to greater than, if lambda equals to greater than minus 1. If it is less than minus 1, so what will happen is that less than or equals to minus 1. So this term would be 1 minus 1, 0. Okay, for equality. So 0 for equality, right? So if lambda equals to minus 1, not 0, it should be, yes, I mean otherwise, if I say just say otherwise, it is undefined, right? Or minus infinity, because if it will be 0, it will be minus infinity. And lambda less than equals to 1 will mean that the function will have minimum instead of maximum, right? So it will be either minus infinity or minus infinity, or it will be like undefined. So since we have minima instead of maxima, so the function will have, since we have maxima instead of minima, so and the function but after putting it less than equals to minus, it will be minima. it will be minimum. So we'll just define it like this, greater than equals to -1. So now we want to maximize the, and it will occur at lambda equals to 2 and x equals to 2. And since we can find this g equal to lambda, we can say that the function is strong duality. So there is the option, right? Strong duality versus something like that. Strong duality holds, strong duality doesn't hold. So strong duality, we can say that it is, since it is like given the optimization problem is convex, and we can see there are points in the relative interior of the domain. So we have points that is interior of the domain. So we can say that the strong duality holds. So if you read more about optimization and all these things, you'll get to know about this more. But in general, if you don't want to learn much about optimization and how this works and how convex things are, you just need to understand the SVM problem. At least in SVM, like we had that problem of non-convex thing in the um, uh, constraint set, and we applied Lagrangian. And when we applied Lagrangian, we have another variable to solve, that is lambda. That's why we found the dual of the. So this is called primal problem. And we found the dual version of the problem, and we solved the dual version of the problem. Using the dual version, we can solve the primal version, and hence we can solve the SVM problem. So if you just understand this, it is fine. If you don't want to go into the optimization much, I don't also have the idea of optimization much. Final question is a theory question. Suppose you have a trend and SVM which is not performing well. So hence you have constructed more feature from existing feature in the model. Which of the following statement is true or false? I think you can say it is like bias or variance question, and you can, I think, variance question, and I think you can solve it easily. So I'm not going to discuss that. So yeah, so we'll end the session for today now. If you have any doubt or anything, like you can ask it later. And yeah, so have anything doubt in today's session? Do you have access to all the recordings that have been published recently? So if you go to, sorry, if you go to my channel, yeah, so if you go to your videos, yeah, so you'll find these things here. It's Introduction to Machine Learning Tutorial 1, 2, 3. And also there are some other content that I taught earlier. Computer networks and internet protocol is there, and computer vision, deep learning for computer vision is there, and deep learning for visual computing, something is there of videos. So yeah, so you can learn, like you can go to this channel and you'll be able to get that. Let me share the code that I wrote as well, as someone asked me.
Can you show that last question?
So I think the notebook is shared as well. So you can go to the shared notebook. Oh, can I show the last question? Yeah, sure. Wait, I'll just chat. Let me paste the code first. Okay, and then I will paste the this channel as well. And the final thing is the question, last question, right? This one. You can find it in the notebook as well, I guess. I've shared the notebooks. Machine learning. Yeah. No, this not Okay, so I'll share the notebooks as well. I think I haven't shared the notebooks yet. This is I pasted my notebook link here as well in the public set to have. The answer to the final question is A and D. Someone get the correct answer. Okay, so we'll end the session today. I think it's a bit late. Bye bye.